Welcome to the course on differential equations models in epidemiology. My name is Steve Schecter from North Carolina State University in the United States. This is lecture 1 on the SIS model. There's an accompanying book to this course, Differential Equation Models in Epidemiology. And this is probably the time to point out that for each lecture, there is an outline of the lecture over here, and the topics will light up as we get to them. So what is this course going to be about? It's about infectious diseases that are transmitted from person to person, diseases like flu or COVID-19, not like malaria, which is transmitted by mosquitoes, and not like cholera, which is transmitted by contaminated water. More precisely, the course is about differential equations models for how these diseases are spread. These are the best developed mathematical models for the spread of infectious diseases. They're the models that are most used by governments and researchers, and you already know a lot of the mathematics that you need to understand them. We're going to start with the simplest classical models, the SIS and SIR models. We'll gradually add complexity and realism. Loss of immunity in lecture 3, asymptomatic carriers in lecture 4, and human response to epidemics in lecture 5. As we go on, we'll learn more about differential equations, the phase line and phase plane in lectures 1 and 2, linearization and planar theory in lecture 3, normally hyperbolic equilibria in lecture 4, and slow-fast systems in lecture 5. For the diseases that we consider in this course, there are two important groups of people: infectives, people who have the disease and can infect others, and susceptibles, people who don't have the disease but could get it. There could be other groups in the population, such as immune people. In the 1920s, two British scientists introduced a simple idea about the rate at which infectives infect susceptibles, and this idea will be at the basis of everything we do. Their idea had two parts. The first part was if you double the number of infectives, a disease should spread twice as fast. Here's one infective sneezing and infecting one person. If you had two infectives and they're sneezing, they can infect two people. The second part of their idea is perhaps a little less intuitive. It is that if you double the number of susceptibles, the disease will spread twice as fast. Here's an infective sneezing and infecting one person. If there's twice as many people running around when he sneezes, he could infect two people. So what does this mean? McKendrick and Kermack thought about this, and they concluded if there are S susceptibles and I infectives, the rate at which a disease spreads should be proportional to the product SI. That way, if you double I, the rate will double, or if you double S, the rate will double. Now let's discuss the SIS model, which is the subject of this first lecture. We're going to consider an infectious disease like the common cold, for which no one ever acquires immunity. We'll consider a population of people who interact with each other, and we'll divide the population into two compartments. That's the term used in epidemiology: susceptibles and infectives. Susceptibles can get the disease and move over into the infective department. Infectives can recover and move back into the susceptible department because we're assuming there's no immunity. Let's let S of t denote the population fraction that's susceptible at time t, and let I of t denote the population fraction that's infective at time t. These are population fractions. S and I are between 0 and 1, and they have to add up to 1, since everybody's in one group or the other. We'll assume, like we said, that the rate at which susceptibles become sick at time t is proportional to the product S of t, I of t, the number of susceptibles at time t and the number of infectives at time t. We're also going to assume that the rate at which infectives become well at time t is just proportional to I of t. In other words, if there were 30 times as many infectives, you'd expect the rate at which they're getting well to also be 30 times as great. The proportionality constants are called beta and gamma. These are typical from epidemiology, and we'll be using them throughout the course. So what are the equations for the rates? ds dt, the rate at which S is changing at time t, is minus beta Si, minus sign because when people get sick, they go from the susceptibles to the infectives, which reduces the number of susceptibles. That's the reason for the minus sign here. And there's also a plus gamma I, because when the infectives become well, that increases the number of susceptibles. The rate of change for the infectives at time t is similar, but the reverse. They increase at the rate beta Si and decrease at the rate gamma I. When the infectives become well, the infective population decreases at this rate. So this is very good, but we're going to use a more compact form. Instead of ds dt and di dt, we'll use S dot and I dot. The dot for derivative with respect to t comes from physics, and we'll use it. And we will not mention that S and I have to be evaluated at time t for the sake of compactness, but you should understand that what this means is S dot at time t is minus beta S of t I of t plus gamma I of t and so on. So what this is, we called it rates. It's really a system of two differential equations. So let's spend some time just talking about differential equations. I know you studied it, but we'll spend some time on it anyway, starting from the beginning. So let's be clear on what the SIS model says and does not say. Here's the SIS model. What it says is if we know the values of S and I at time t, we know their rates of change at time t. That's an instantaneous fact. What this model does not say, at least not immediately, is what's going to happen. Is the disease going to oscillate in prevalence? Will the disease tend toward a constant prevalence? Will the disease die out? These equations at the moment don't tell us any of that. The SIS model is absolutely typical of models that are used in Western science since Isaac Newton. In the 17th century, Isaac Newton introduced a basic idea. Here's his idea. Our understanding of the world is usually an understanding about rates, as with the SIS model. Our understanding about rates can be expressed as a system of differential equations, and it's the solutions of the system of differential equations that are going to tell us what actually happens. Differential equations, since Newton, are the language of Western science. What is a differential equation? Let's start with a moving point in Rn. So x of t, the position of that point at time t, is x1 of t through xn of t. Those are the n coordinates of the point at time t. The velocity vector of this moving point would be x dot of t, the dot notation. The coordinates are just the derivatives with respect to t of x1 of t through xn of t. The velocity vector is always drawn with its tail at x of t. So for example, Here's an example in the plane. Suppose x of t is cosine t sine t. So what this is we start at 1, 0, at time 0, and we just move steadily around a circle. At time 2 pi, we're back where we started from, and we just keep moving. The velocity vector at time 0 is vertical. Its length tells you the speed. At time 2 pi, we're here, and the velocity vector is horizontal. So what a differential equation tells us is, if we know x, a point that represents the state of the system, then we also know x dot, how x is changing. In other words, a differential equation tells us the velocity vector x dot as a function of the state x. X dot depends on, is f of x. X is in Rn. If you wrote this all out in lots of equations, expanded it, x1 dot would be a function f1 of x1 through xn, x2 dot would be and so on, xn dot would be a function fn of x1 through xn. This is a differential equation if you write it this way, or if you write it this way, it's usually called a system of differential equations, but it's really the same thing. Different ways of writing the same thing. A solution of x dot equals f of x is just a function x of t, such that x dot of t is always exactly what the differential equations says it should be. X dot of t is f of where you are at time t, f of x of t at every time. So let's give an example, which will relate to that earlier curve that we just drew a picture of. Our differential equation will be x1 dot equals minus x2 dot equals x1. This is in the plane system of two differential equations. I'm not going to tell you how to find solutions. You may know. I'll just tell you one solution. One solution, there are many, is the curve we were looking at before. x1 of t, x2 of t is cosine t sine t. Why is this a solution? Even if you don't know how to find it, you can easily know how to check it. To check it, you just plug into both sides of the differential equation and check. So here for x1 dot, we plug in the derivative of cosine t, which is minus sine t. And here for minus x2, we plug in minus sine t. There it is. Two sides are equal at every t. In the second equation, here we plug in x2 dot, which would be the derivative of sine, cosine t. There it is. And over at the right, we plug in x1, which is cosine t. They're equal at every t. So that's a solution of the differential equation. There are many others. An equilibrium of x dot equals f of x is a point where f is 0. If you have an equilibrium of a differential equation, then it's easy to tell you what one solution of that differential equation is. One solution is just stay at the equilibrium forever. X of t equals x1. It makes sense because the derivative of this constant is 0, and that's what the differential equation says that x dot should be. For any differential equation, the equilibria are going to be important points. If we have a differential equation, what is it that we want to do with it? Just think about its role in Western science. Assuming we know the state of the system at some initial time, what we want to do is use our differential equation to predict the state of the system in the future. In other words, if we have a differential equation, x dot equals f of x, and an initial condition, x at time t naught equals x naught, we want to find a solution x of t of the differential equation whose value at time t naught is the given point x naught. This is called solving an initial value problem. So for example, for this differential equation we just wrote down, suppose we had the initial condition x1, x2 at time 0 is the point 1, 0. Again, you may not know how to find the solution of that initial value problem, but if I tell you what it is, you can certainly check that it's right. The solution happens to be our old friend, x1 of t, x2 of t is cosine t sine t. So what do you have to do to check that's a solution of the initial value problem? You have to check that it's a solution, which we already did, and you have to check that it satisfies the initial condition. So what is x1 of 0, x2 of 0? Just plug in here. It's cosine 0 sine 0, and sure enough, that's what it's supposed to be, 1, 0. So this is a solution of that initial value problem. For differential equations actually to be useful in science, it is important that initial value problems should have solutions, and the solution should be unique, so that we can use the differential equation to make a unique prediction about the future. And fortunately, that's true for all the differential equations one normally encounters. So here's the basic theorem. Suppose f from Rn to Rn is a continuously differentiable function, and x naught is a point in Rn. Consider the initial value problem, x dot equals f of x, f's continuously differentiable, and x at some time t naught is x naught. Our theorem says that initial value problem has a unique solution. And I'll throw one more thing into this theorem that's often useful. If that solution stays in a compact set, that means a closed and bounded set as time increases, then x of t is defined for all future time. The solution never stops being defined. Actually, the same is true if the solution stays in a compact set in backwards time, then it's defined for all backwards time for time going to minus infinity. Now, there may not be a formula for the solution. You may not be able to find a formula for the solution. Perhaps it's impossible to find a formula for the solution, but the solution is still there and it can be approximated numerically. So back to our SIS model. Here it is. I hope you remember it. S is susceptibles, I is infectives. One thing to notice about this model is that if I add S dot and I dot, everything cancels and I get 0. Now, when the derivative of a function is 0, that function is constant. So if we add S of t and I of t, the total is always constant. In fact, that constant is 1. If S plus I is 1 initially, then S plus I is 1 always. And that's very good. Without that, we'd have a bad model. S and I are supposed to be population fractions. They should always add up to 1. But what that means is we really only need one of the equations. We're just going to use the I equation, because if we can just figure out I of t, then we know S of t without using any differential equations. S of t is just 1 minus I of t. So we're just going to use the equation for I dot. So I dot is beta S. Now, if we just have one equation for I dot, the entire right-hand side should just have I's in it, not S's. So what we're going to do is substitute for S 1 minus I. So I dot will be beta times 1 minus I minus gamma I. And we're just going to multiply this out. It's beta minus gamma I minus beta I squared. So you can see that I dot is just a quadratic differential equation. It's quadratic in I. A simple way to see what the solutions do is not to go and try and calculate them, but to just draw what's called the phase line. The phase line is the I-axis with a right arrow wherever I dot is positive, a left arrow wherever I dot is negative, and a dot wherever I dot is 0. That's an equilibrium. Remember, we said those points were important. So let's draw the phase line for I dot equals beta minus gamma I minus beta I squared. And perhaps it's easier to factor out the I. Then you'd have beta minus gamma minus beta I times I. This makes it easy to see where the equilibria are. The equilibria occur where the right-hand side is 0. In other words, where I is 0, that's 1 point, and where this term is 0, if I set this equal to 0 and solve for I, I'll just get beta minus gamma over beta. Or in other words, 1 minus gamma over beta. So those are the two equilibria. So here's the I-axis. Where are those two equilibria? One is at 0, right here. And the other is at 1 minus gamma over beta. And now there's two cases. If gamma over beta is bigger than 1, then 1 minus gamma over beta is negative, and that second equilibrium is over here, negative. On the other hand, if that's gamma over beta greater than 1. If gamma over beta is less than 1, then 1 minus gamma over beta is going to be in between 0 and 1. And so in between 0 and 1, we'll have a second equilibrium. Now, what is the direction of the arrows? Well, some people could just figure this out by thinking about this little formula. If it's a little hard for you to figure out, just look at it this way. The equation for I dot as a function of I is just a parabola that's upside down because of the minus sign. So if I made an I dot axis here going through 0 and graphed I dot as a function of I, it would just be a function, it would just be an upside down parabola, and it goes through these two equilibria. Okay, so what that shows you is where I dot is positive and where it's negative. Where I dot is positive and where it's negative. Now, for our purposes, we only care about I between 0 and 1. Here in each case between 0 and 1. So let's just focus here on I between 0 and 1. That's what's important to us. Okay. What do these phase lines have to do with initial value problems? So what this shows you, for example, is that if your initial condition was right here, what would happen as time increases is you would just move in this direction. You could never hit the equilibrium because, as we saw, if you're at the equilibrium, you must have been there forever. You never hit the equilibrium. That means you're staying in a compact set. So the solution is defined for all time, which means that if I start here, as time increases, I just head towards 0. As time goes to infinity, I never quite get there. Over here, where gamma over beta is less than 1 and there's an equilibrium in the middle, if I start here, as time increases, I head to the equilibrium. If I start here, as time increases, I head to the equilibrium. So the phase line doesn't give you as much information as there is in a solution. It doesn't tell you exactly where you are at time t, but it does tell you pretty well, if you start at a certain point, what you're going to do. What it tells us is, if gamma over beta is greater than 1, the disease is going to die out. It's going to head to 0. Number of infectives will head to 0. And if gamma over beta is less than 1, it doesn't matter where you start. The prevalence of the disease will always head toward the same number, 1 minus gamma over beta. In this case, what they say in epidemiology is that the disease is endemic in the population. It's always present at this fraction. So that's our conclusions about the SIS model. But to really understand what these conclusions mean, we just use beta and gamma to be constants of proportionality. To really understand this, we need to understand what beta and gamma actually mean. It turns out that they both have meanings that we can understand, and that will help us to understand the meaning of this fraction, these fractions here. Okay, let's start with what beta means. And to understand what beta means, we need to forget population fractions and look at the SIS model without population fractions. So we're going to consider a population of constant size n. We're not going to consider births and deaths in the population. T will be time in days. That's what's usually used in epidemiology. We're going to use little s of t for the number of susceptibles at time t. So it's just a number of people. It's not a population fraction. We use little I of t for the number of infectives at time t. And little s plus little I will always add up to n, the population size, instead of 1 when there were population fractions. Let's think about the rate at which the disease is transmitted. And what we're going to think about is how one person, one infective, transmits the disease to other. So we want to look at how many new infective people one infective person causes in a day. New infective persons per infective person per day. So one way to think about that, one way to break it down, is look at how many susceptibles come into contact with that infective person per day, and then multiply that by the probability with which the disease is transmitted. Okay, so let me say a little about what I mean here. What do I mean about an infective person contacting the susceptible? That depends on the disease. That means you come into contact with the susceptible in a way in which the disease would normally be transmitted. If the disease is COVID-19, that means that you're close to the susceptible, you're breathing, and probably indoors and not outdoors. When you're outdoors, the germs you breathe get dissipated and there's not much probability of transmission. So you come into contact with the susceptible in a way that would normally transmit the disease. But as we know, even if you got a cold and walk right up to somebody and cough in their face, they don't necessarily catch the cold. There's some probability of transmission, and we have to multiply by that. That'll vary. It's different for different diseases. Okay. Now let's look a little more in detail at the rate at which an infective person contacts susceptibles. The way to think about that is the rate at which an infective person contacts susceptibles, or the number of susceptibles an infected person will contact in a day. Look at all the people that he contacts in a day. And again, by contact, I mean the contact that would normally spread the disease in question. And then multiply by the fraction of the population that's susceptible. And that should be the number of susceptibles that the infective contacts in a day. For example, if he contacts 3 people in a day, but only a third of the population is susceptible, then he's only contacting 1 susceptible per day. Okay. So now we're going to substitute our second formula into the first. Let's go back a slide. Here's our first formula for the new infective persons caused by 1 infective person in a day. It's got contacted susceptibles per infective person per day in it. And so we're going to substitute for that this expression that we just figured out. We'll just take that and stick it right in there and get a new expression for the new infective persons per infective person per day. So here's our new formula. The new infective persons caused by 1 infective person in a day is the contacted persons per infected person per day multiplied by the percentage of the population that's susceptible, and then multiplied by the probability of transmission. So now we're going to, using that formula, we're going to define a number beta. And I'm using beta for this number because it's going to turn out to be what our previous beta was. Beta is going to be this expression times this expression. In other words, the part here that doesn't change with time as the number of susceptibles in the population changes with time. So beta is contacted persons per infected person per day times probability of transmission. That's what it is. Now, another way of thinking of that is that's what new infective persons per infective person per day would be if the entire population that was susceptible, if S was N, this would cancel. So beta is the new infective persons per infective person per day, provided everyone is susceptible. It's the number of people an infective infects every day, right at the beginning of an epidemic when everyone in the population is susceptible. And therefore, we can figure out a formula for I dot in this new situation where we're looking at the population of size n. So what is I dot? It's a rate per day. We look at the new infective persons that one infective person causes in a day. That's what we just got a formula for. But that's just how many one infective person is causing. We have to multiply by the number of infectives they're all, because they're all doing this, right? And that would be I dot, the new infective persons per day, except that we also have to subtract the rate at which infectives are getting cured and moving back to the susceptible population. And we'll use our old friend gamma for that, minus gamma I. So if I substitute for here, beta times S over n, what this is just beta times S over n times I, this first term here. Right. This new infective persons per day is just this stuff, which is beta times S over n. Then we've got the I, and then we've got minus this other. It's great. Here's what we just figured out. I dot was beta over n SI minus gamma I when we look at a population of size n. That's what we just figured out on the previous page. And similarly, S dot would turn out to be the exact opposite of that, a minus sign here and a plus sign here. Now, our point in doing this was to understand beta and gamma back when we were looking at population fractions. So let's go through that. How does this all relate to population fractions? Here's the population fractions. Capital S is just little s over n. That's the fraction of the population that's susceptible. Capital I is just little I over n. That's the fraction of the population that's infective. Another way to put that is little s is capital S times n if I multiply through by n. Wrote that here. And if I multiply through by n here, little I is n times I. So I take these expressions and I just substitute them back into these differential equations to get a differential equation for the population, to get differential equations for the population fractions. So let's just go through substituting into the first equation. Little s dot is just going to be, n's a constant, little s dot is just going to be n times capital S dot. So I substitute that. Next, I've got beta over n. Then for little s, that's ns. So I substitute that. Little I, that's ni. So I substitute that. Plus gamma little I. So for the little I substitute the ni. Then I take this equation and I just want to simplify it. So I divide it through by n, and then I'll get s dot equals, and when I divide by n, I'll be dividing by n squared, multiplying by n squared. The n's will cancel here. I'll be dividing by n, multiplying by n. The n's will cancel here. And I'll just get s dot equals minus beta si plus gamma I. Our old friend, that's the equation for the population fractions. I dot works the same way. So we're back where we started from, except that now we know what beta means. Beta is the number of people an infective would infect per day if everybody was susceptible. Okay. Great. Now let's turn to what does gamma mean? So this is something you may have learned about if you learned about exponential functions in a probability class. It's not really special to infectives, but let's go through it for infectives. So let's just think about infectives getting well. Let's forget about them getting diseases. Let's simplify everything here. So here's how infectives get well. I dot is minus gamma I. And for simplicity, let's assume that we start with everybody infected and people are just going to get well at this rate minus gamma I. So this is an initial value problem, a differential equation with an initial condition. The solution happens to be I equals e to the minus gamma t. Okay. So you can notice right away that I goes to 0 as time goes to infinity. That's because everybody eventually gets well and the infected population decreases towards 0. I dot is minus gamma, e to the minus gamma t. It's negative because I is decreasing as people get well. The rate at which people get well is the opposite of this. It's gamma e to the minus gamma t. It's positive because the well population is increasing. In fact, if you integrate this derivative from time 0 to time infinity, you will just get 1. I'm going to leave you all to work through these things on your own using the calculus you remember. And what this population means, if we integrate the derivative at which the rate at which people get well from time 0 to infinity, we get 1 because eventually everybody gets well. Now, when you have a positive function like this on a time interval, in this case 0 infinity, whose integral is 1, it's what's called a probability distribution on the interval. In this case, the interval is 0 to infinity. And one thing you learn in calculus is that if you got a probability distribution on a t interval, if you integrate t times the probability function over the interval, you'll get the mean value of t. In this case, the mean value of t is 1 over gamma. But what does that mean? People who get well at time t, remember we assumed everybody was sick initially, they were sick for time t. So when we say that the mean value of t is 1 over gamma, what we're saying is that 1 over gamma is the average length of time that people are sick with this disease. That's the meaning of gamma. 1 over gamma is the average length of time that people are sick with our disease. If you had a cold that kept you sick for 5 days, 1 over gamma would be 5, so gamma would be a fifth. All right, let's take what we just learned and go back to our fundamental conclusions about the SIS model. We said that if gamma over beta was greater than 1, the disease died out. If gamma over beta was less than 1, the disease becomes endemic. It turns out to be better, as we'll see in a second, to look at beta over gamma, not gamma over beta. So let's just re-express this. If beta over gamma is less than 1, then gamma over beta is greater than 1, and the disease dies out. If beta over gamma is greater than 1, then gamma over beta would be less than 1, and the disease would become endemic. So what's nice about beta over gamma is that we now know exactly what beta over gamma means. Beta over gamma is beta times 1 over gamma. Beta is the new infective persons per infective person per day, provided everyone was susceptible. 1 over gamma is the number of days a person's infected. So if you look at how many people an infected person infects per day and look at the number of days he's infected, multiply that out, you'll just get the total number of people that that infective person infects. So when you multiply this out, you get the total number of new infective persons caused by one infective person, provided everybody was susceptible. And that product is called, in epidemiology, R naught. The product beta over gamma is called R naught in epidemiology. You've heard of R naught, I'm sure. It's used in newspapers sometimes in discussing the COVID-19 pandemic. R naught is calculated not just for the SIS model, but for other models. It's the most important number in mathematical epidemiology. It's the number of new infective persons caused by each infective person when everybody's susceptible. So for the SIS model, what does that say? Remember, this was the I-axis. So I equals 0 is when there's no infectives, when everybody's susceptible, so to speak. So when R naught's less than 1, if the disease entered the population, if the infectives became slightly positive, each infective is replacing himself with less than 1 infective person, the disease dies out. When R naught's greater than 1, if we started near here with almost everybody susceptible, near 0 infectives, if a disease entered the population, then each infective would be replacing himself by more than 1 infective person, and the disease would start to spread. As it spreads, the number of susceptibles decreases, that rate of transmission is going to decrease, and we're going to head toward this endemic population fraction. Okay, we're at the end of our lecture. We've talked a lot about the SIS model. Let's stop and ask ourselves, is it correct? So you may have noticed a few fishy things, using differential equations for taking derivatives when there's only a finite population. That's sort of standard math stuff. Let's not worry about that. You did that in your calculus course. The important thing is that we assumed that a disease spreads at a rate proportional to the product SI. Is that correct? So what that assumption might remind you of is a well-stirred solution in chemistry. In chemistry, you have what's called the law of mass action. If a solution contains 2 reactants and the solution is well stirred, then the rate of the reaction is proportional to the product of the concentrations of the 2 reactants. Very much like what we're doing here when we use the product of S and I. So in chemistry, this is correct for a well-stirred solution. What's the analog of a well-stirred solution in chemistry? It's what's called a well-mixed population in epidemiology, a population in which people are mixing up and just encountering each other randomly. So for a population like that, the SIS model is correct. Now, are populations normally well mixed? And the answer to that is no. In a human population, people don't encounter everybody else randomly. Even if we take for one city, the unit that we're discussing, not a country, you don't encounter other people in your city randomly. You Perhaps you go to school and encounter people at your school, preferably. You encounter your family, you encounter people in your neighborhood. You don't encounter everybody in the city at the same rate. So the SIS model is incorrect. There are other models used in epidemiology that attempt to get around this, but they're much harder to deal with. The English statistician George Box once said, all models are wrong, but some are useful. And that's true of the SIS models and the other differential equation models that were useful, that we're going to see in this course. They are not exactly right when you delve into it, but they're pretty good, not 100% good, but pretty good in practice. And that's why they're used in practice. Thanks very much. That's the end of lecture 1.